Scientists just cracked one of chemistry's most stubborn puzzles, and it could completely revolutionize how we think about carbon-based materials forever. Imagine trying to build a house of cards in a hurricane. That's essentially what researchers at Oxford University faced when attempting to create a new form of carbon that wouldn't instantly fall apart at room temperature. But here's where it gets controversial. They didn't just succeed. They've opened the door to possibilities that some scientists thought were impossible just decades ago. A groundbreaking team, led by Oxford University's Department of Chemistry, has achieved what many considered a near-impossible feat. They've successfully created and stabilized a brand new molecular form of carbon called cyclocarbon. This isn't just another laboratory curiosity. It's a complete game-changer that challenges everything we thought we knew about carbon's limits. But what makes this discovery so extraordinary? Picture 48 carbon atoms arranged in a perfect ring, with bonds alternating between single and triple connections in a precise pattern. This molecular structure, while theoretically possible, had never been stable enough to study under normal conditions, until now. The significance of this achievement becomes crystal clear when you consider the rarity of such breakthroughs. Since 1990, when scientists successfully synthesized fullerenes, those soccer ball-shaped carbon molecules you might remember from chemistry class, this represents only the second time researchers have created a new type of molecular carbon allotrope that can be examined under everyday laboratory conditions. Think about that. In over 3 decades of intensive research, only 2 such discoveries have emerged. And this is the part most people miss: the ingenious solution the Oxford team developed to overcome carbon's natural instability. They created what scientists call a catenane structure, essentially threading the delicate carbon ring through 3 protective molecular guards that shield it from destruction. It's like putting a fragile antique inside multiple protective cases, each one adding another layer of security. Dr. Yueze Gao, the study's lead author, explains the breakthrough in terms that highlight its practical importance. Achieving stable cyclocarbons in a vial at ambient conditions represents a fundamental stepping stone. This breakthrough will dramatically simplify the process of studying their reactivity and properties under standard laboratory conditions. But here's where the controversy begins to simmer. Previous attempts to study these pure carbon rings required either gas phase conditions or temperatures so extreme they approached absolute zero, specifically between 4 to 10 Kelvin, which is colder than outer space. The Oxford team shattered these limitations by creating a cyclocarbon that remains stable in liquid solution at a comfortable 20 degrees Celsius, 68 degrees Fahrenheit, with an impressive half-life of 92 hours. The methodology behind this success involved 3 critical innovations that some traditional chemists might find surprisingly unconventional. First, they strategically selected a larger cyclocarbon structure that experiences minimal strain, essentially choosing a size that nature finds more comfortable. Second, they developed remarkably gentle reaction conditions for the crucial unmasking step, where a precursor molecule transforms into the final product without causing destructive stress. Third, they employed those protective threaded macrocycles that act like molecular bodyguards. Professor Harry Anderson, the study's senior author, reveals the human story behind this scientific triumph. This achievement represents the culmination of an extraordinarily long journey to synthesize cyclocarbon catenanes, driven by our hope that they might prove stable enough for room temperature study. Our original grant proposal dates back to 2016, building upon preliminary results from 2012 to 2015. Reaching this milestone brings tremendous satisfaction, especially considering the numerous moments when our goal seemed completely unrealistic and unachievable. The verification process employed multiple sophisticated analytical techniques that leave no doubt about the structure's authenticity. Mass spectrometry, nuclear magnetic resonance, NMR, ultraviolet visible spectroscopy, and Raman spectroscopy all confirmed the successful synthesis. The most compelling evidence came from a single intense carbon-13 NMR signal representing all 48 carbon atoms, proof that every carbon atom exists in an identical environment within the ring structure. The collaborative nature of this research demonstrates how modern scientific breakthroughs require diverse expertise. Teams from the University of Manchester, University of Bristol, and the Central Laser Facility at Rutherford Appleton Laboratory contributed essential knowledge and resources to make this discovery possible. The implications extend far beyond academic curiosity. Oxford University's track record speaks volumes about the potential commercial applications. They're the UK's leading university patent filer and have spawned over 300 new companies since 1988. With more than a third emerging in just the past 5 years, this cyclocarbon breakthrough could potentially spawn entirely new industries focused on carbon-based materials with previously unimaginable properties. But here's the question that's dividing the scientific community. Are we prepared for the revolutionary applications this discovery might unleash? Some researchers argue that stable cyclocarbons could lead to materials with unprecedented strength, conductivity, or optical properties. Others worry about rushing into applications before fully understanding the long-term implications. The timing of this publication in Science magazine on August 14, 2025, couldn't be more significant, as we face global challenges requiring innovative material solutions, from renewable energy storage to advanced computing. This breakthrough arrives at a critical moment. Yet controversy surrounds the broader implications. If scientists can now easily study and manipulate these exotic carbon structures at room temperature, what limits remain on carbon-based material design? Are we approaching a new era where the periodic table's most versatile element reveals capabilities we never imagined? This discovery challenges a fundamental assumption that has guided materials science for decades: that exotic molecular structures must remain laboratory curiosities, too fragile for practical study or application. The Oxford team has shattered this barrier, potentially opening pathways to materials that could revolutionize everything from electronics to energy storage. What fascinates researchers most isn't just what they've accomplished, but what questions this breakthrough raises. If cyclocarbon can be stabilized through catenane formation, what other impossible molecular structures might become accessible? Could we be standing at the threshold of a new materials revolution? The achievement also highlights the importance of persistent, long-term research vision. Professor Anderson's admission that their goal often seemed unrealistic and unachievable reminds us that today's impossible dreams might become tomorrow's revolutionary realities. So here's the thought-provoking question for you. In an era where scientific breakthroughs often promise to change everything, does this cyclocarbon discovery represent genuine transformation, or are we getting carried away by the excitement of scientific novelty? Do you believe stable room temperature cyclocarbons will truly revolutionize material science, or will practical limitations keep them confined to academic laboratories? Share your thoughts. Are you optimistic about the revolutionary potential, or skeptical about the real-world applications?